Alright, so last time we talked about the definition of a derivative, which looks like this. And this part on the right was the difference quotient. And then now that we've had some experience with limits, we substituted the direct substitution with plugging in 0 for h or 0 for delta x, same thing. And we were able to find the instantaneous rate of change. So we talked a little bit about what problem that solved, what type of questions we can now answer that you couldn't answer before. But as you saw from your practice, simplifying this difference quotient is often pretty time consuming. So when there's reasonable shortcuts, we certainly want to take those. And that's what this section's about. This section is about the basic differentiation rules. So the ones that we use often enough that the shortcuts are reasonable to just know things. So that's what we're going to try to address today. All right, so the first one is the constant rule. If you take the derivative of a constant, it will equal 0. Now to me, this one should make sense to you if you think about the graph. So like if I'm trying to find the derivative of 6, well, 6 is a horizontal line. So no matter where, it doesn't matter what x value you're looking at, the slope is always 0. If it was -2, it would just be a different horizontal line. And again, no matter what x value you pick, you always have instantaneous slope of 0. So notice how there's no x in there because it doesn't change. It's constant. It's just always this one thing. So anytime you take the derivative of a constant, it will be 0. So think about those graphs, and I think that should make sense to you. All right, then we've got the power rule, and the power rule is one that we use all the time, probably the most common one. And in a textbook, this is what it looks like. And it's saying if you want to take the derivative of x to the n, you would get n times x to the n minus 1. Okay, so that's kind of a mouthful to say it that way. So instead, what people usually say is if you want the derivative of 2x, you're going to bring the power down. So in this case, it's like they're bringing down the n. And then you lower the power by 1. So if it was n, it becomes n minus 1. And so for me to lower the power by 1, you get 1. And so there's this derivative. Now again, of course I could do that with the definition of a derivative, but since the power rule consistently works for us, that is so much faster. Okay, so another example, bring the power down, lower the power by 1. So the derivative of 8x to the 7th is, or I'm sorry, of 8x, x to the 8th would be 8x to the 7th. A little bit of a tongue twister there. All right, so x to the 5th, bring the power down, gives you a 5 out front, and then lower the power by 1, leaves you a 4. So the derivative of x to the 5th would be 5x to the 4th. And I mean, something crazy like x to the 1000th, obviously not going to come up very much, but the power rule is still easy to apply. Bring the power down, lower the power by 1, there's its derivative. Now just imagine, don't actually do it, but imagine that if you had to use the difference quotient on that, appreciate like you would have to take x plus h to the 1000th power, and you'd have to multiply it by itself 1,000 times. So that would be very, very time consuming and completely unnecessary because we do have this power rule. All right, we've got constant multiple. And the constant multiple rule says if you've got a number times a function, that's the same thing as a number times its derivative. So this is kind of nice because it allows us to get numbers out of the way. So like this 2, you can just think of it being brought out front. Okay, so this would be like 2 times the derivative of x squared. So in the end, you end up with 4x. Now on this one, you don't actually need to think of the constant rule, but there are times that you need to. So just to show you that you get the same thing, you could do the power rule here too. Bring the power down, and so you'd multiply it by what's already there, and then you'd lower the power by 1. So either way, you end up with 4x. Okay, so this one would be 3 times the derivative of 8 to the x. So apply the power rule, and then just like multiplying the 3 in the end, comes out being the same. Again, to me, I just think of this kind of as a convenience thing because it allows me to simplify what I'm trying to take the derivative of, and I can do the multiplication later. Okay, I can pull the 1/2 out front, bring the power down, lower the power by 1, and then just multiply it back through. Again, these aren't necessarily the best examples because really you could just think of power rule only on these and it would be fine. Okay, so 4 times this derivative, and then I could say this was 4,000. Okay, so that's how the constant rule applies. All right, sum and difference rules, also one that's very convenient. It says if you want to take the derivative of a function plus another function, then just take the derivative of the first one and then add the derivative of the second one. Or if it's subtract in the middle, do the same thing but do subtract. So this allows us to split it up into multiple smaller pieces. So what I mean by that is if I want the derivative of all of this stuff, I can just worry about doing the derivative of this, which would be the power rule, and then this is a plus, so this will be a plus, and then I'll do the derivative of this one, which is also power rule. So I can just do the derivative one term at a time, and allows me to split it up. Subtraction works the same way. Derivative of this, derivative of that, and that's it. Okay, so if you'd pause the video and try out this one with 4 terms, do all that and see what you get for an answer. Okay, so a derivative of the first piece after power rule would look like this. Second term would look like this. Third term would look like that. And finish off with the last term would look like this. Okay, so pretty intuitive. You'll get used to this and it'll just be second nature to you pretty soon. All right, and then we also look at some trig functions. So we actually do need to know the derivative of all 6 trig functions and also some of the inverse trig functions, but that'll be for another day. But to get you going here, you do have to memorize the derivative of sine and the derivative of cosine. So the derivative of sine is cosine, but the derivative of cosine is negative sine. So you got to come up with something for yourself to remember. One of them, they change to the other one, but when you change cosine to sine, it does get multiplied by a negative. Changing sine to cosine, you don't multiply by a negative. Okay, so these are often pretty easy pieces. As long as you know the derivative of cosine is negative sine, you're done. As long as you know the derivative of sine is cosine, that would be easy. Okay, and then we can kind of mix in some of the other stuff we've talked about. So the derivative of cosine is sine, and then I can do the derivative of sine is cosine. So that would be like the what do they call it? The difference rule. Looks like just doing this, but that way I can test you to see if you know both of them. Or the constant rule. So 3 times sine, its derivative would be 3 times cosine, and minus 4 times cosine would be 4 times sine times a negative, because the derivative of cosine gives you a negative, and there was already a negative sitting there. Okay, so not hard to use, but again, if you don't have it memorized, you're kind of stuck pretty early. All right, next up we've got derivative of a natural exponent function, which is just like e to the x. And e to the x is one of the very few functions that is its own derivative. The derivative of e to the x is e to the x. And because of that kind of neat relationship, this does come up all the time in calculus. So derivative of e to the x is e to the x. Nothing more to it. If you had 5 times it, then it would be growing 5 times as fast, so its derivative would also be 5 times bigger. Okay, this one, 2e to the x minus 5e to the x. derivative of e to the x stays e to the x. All right, and then you need to recognize the derivative of a natural log function. So remember, logarithmic functions have different bases. Natural log is the one that is log base e. So anytime you see the natural log and you need to take its derivative, you have to know that that is 1 over x. Okay, feel free to do the definition of a derivative and try to simplify it if you'd like to discover where it comes from. But for our uses, we just want to go straight to that because we're going to use it all the time. So derivative of natural log of x is 1 over x. If I wanted to multiply by 2, then multiply the derivative by 2. Okay, and do the same thing here. This would be 2 over x. This would be minus 4 e to the x. And this would be minus 8 sine x. Okay, so make sure you understand each of those terms before you move on. All right, we've also got derivatives of logarithmic functions that don't have a base of e. Natural log is when you have a base of e, but most of the time you've got other things like base 3, base 8. Well, I say most of the time. Most of the time in previous courses, I would say they're not normally natural logs, but in calculus, it's usually a natural log. Okay, so what it says, you should do 1 over a, and a is the base, and then in the denominator, you want a natural log of b. So if I wanted the derivative of this, it'd be 1 over 3 natural log of whatever that is, or 1 over 8 natural log of this. Okay, this one I want you to pause, and I want you to try to apply that to this question, see what you get. Okay, so there's a couple ways for you to do this one. So what I kind of suspect that you did, since I didn't give you any hints, is if you apply this to this, you would get 1 over e to the natural log of x, and this would be 1 over 9 natural log of x. So while this, I guess, is technically correct, this stuff here on the left is much messier than it needs to be. So if we tried to apply some of our properties of logarithms, one of the things that you should remember is that this can go back and forth. This can go up as an exponent, or it can be brought down not as an exponent. Okay, so I could bring that up like that. And then I could say, well, natural log is really just log base e. And so then this is asking you e to what power, or e to what power gives you x to the e. Okay, so you get kind of bogged down in some of the logarithm rules, and I think we could probably piece that together. But really, I wanted to show you enough of that to show you that that's not really a good approach. Really, what's a good approach is to say, wait, log base e is just natural log, and a natural log derivative is 1 over x. So all of that mess would have simplified to 1 over x if I had stuck with it. But as a multiple choice question, you've got to be able to recognize that if you took that approach. What makes more sense is just know whoa, okay, a little bit of a jump there. You must remember log base e is the same thing as natural log. Very important. Makes your life a lot easier there. Okay, so all these are some slight variations of different things to use, and I mentioned that power rule is going to be the one that's used the most, but sometimes power rule's not ready to go. Like these first examples I gave to you were set up where I just had to bring the power down, lower the power by 1, bring the power down, lower the power by 1, do it again and do it again. But if you look at these examples where you're at, that doesn't make sense. You can't just bring the power of 2 down. 2 is an exponent on x that's in the denominator, so it doesn't look right yet. So what you're going to have to do is you're going to have to apply some exponent rules. And so you're going to have to say, wait, an exponent of positive 2 in the denominator is the same thing as an exponent of negative 2 in the numerator. Now, 99% of the time when you've seen this in the previous course, you would always make the negative exponent move to the other side of the fraction and become positive. But for our uses, we want to do this. We want to move it to the other side because now it's in a format that makes sense to me for power rule. I can bring the power down out front, and then I can lower the power. One thing you do need to be careful about, though, is negative exponents are almost always considered unsimplified, so you would need to bring this stuff back down to make it be positive. Okay, so power rule wasn't ready to go, but rewriting it with an exponent rule, it was. So, same idea with this. The fifth root of x is like x to the 1/5. And as long as you remember that about radicals, the power rule says bring the power down. Actually, I better do it down here. Bring the power down, lower the power by 1. And again, don't leave negative exponents. If this is in the numerator as negative 4/5, that's the same as being in the denominator with positive 4/5. So it takes some algebraic manipulation before you can apply the power rule. Okay, and then for this one, this is like x to the 1/2 over x. And so when you multiply things with the same base, you like to add the exponents. In this case, we're dividing things with the same base, so we would subtract the exponents. And that would leave me with x to the negative 1. Oops. X to the negative 1/2. Okay, and that's just the algebraic manipulation. I haven't really taken a derivative yet. Now derivative, bring this down out front, lower the power by 1, and because that is a negative exponent, make sure you move it to the denominator and make it a positive exponent. Okay, so power rule, very straightforward, but since we have to know all this other stuff from previous math courses, and it's not always obvious what to do, or maybe you just forget one of those exponent rules temporarily, then that makes it a touch harder. Okay, so moving on, you also need to know a little bit about horizontal tangent lines. So horizontal tangent lines often represent something, or if your function represents something in a real world situation, so I don't know what this graph represents, but pretend like it's real data. Horizontal tangent lines are usually points of interest. Something's changing there. It's going down and then it stops and probably goes back up, or it's going up and then it starts going back down. So horizontal tangent lines have a slope of 0. Okay, so imagine this graph represents the distance you are away from home for a given time. For what values or when or where do you think the graph has a tangent line with a slope of 0? So like right here, this is certainly not a tangent line of 0. That tangent looks pretty negative. So right here, that looks to be a tangent line of 0. Right there it has a horizontal tangent line, and right there it looks like it has a horizontal tangent line. At those three instances, at, let's see, 1, 3, and 5, it appears that the slope is either the slope of the tangent line is going from decreasing to increasing, decreasing to increasing, or it's going from decreasing to decreasing. But at that instant, at these instances, it's temporarily 0. All right, so if you would, go ahead and pause the video and ask yourself, what does that mean in the context of this made-up question? Okay, so if this is the distance you are away from home, it looks like this person was, I don't know, 2 miles, 2 feet, whatever, away from home, and then it gets less and less and less and less and less, and then at this time, 1 second, 1 minute, 1 hour, whatever these units are, there was a time where their distance was not changing. So I would probably say all of these is when the person stopped moving. Person was staying still. Okay, so either they stopped walking, they stopped their car, whatever, but they weren't getting closer or further away from home at those three instances. So for whatever, I mean, I don't know the context of the question, but something's probably going on at those times. It's not going on at the other times, and so that's why we usually care about these horizontal tangent lines. So if you think about these in context of the derivative, all of those have a derivative of 0, because the derivative represents the slope of the tangent lines, and horizontal lines have a slope of 0. So at that instant the slope was 0, this instant the slope was 0, and this instant was the slope of 0. So you've got to be able to look at a graph and recognize that. Okay, so not just looking at a graph, but you also need to be able to look at a function and determine where, if at all, a function would have horizontal tangent lines. So I guess if you had a calculator, if this was like a calculator question, you could graph it, and then you could see a graph just like this one, and then you could hopefully look and see what you need to get out of it. But that's sometimes time consuming, and most of the time you would have a calculator to do that for you. So instead what you're going to have to say is, wait, horizontal tangent lines occur when the derivative equals 0. Well, I can find the derivative with the power rule and the power rule. Bring this power down, lower the power by 1, anything to the 0 power. Anything to the 0 power is 1. So I know, or I can tell you what the derivative is, and the derivative will tell me the slope for any x value that I want, and I want to know, is the slope ever 0? So you could set it equal to 0, and now it's looking a lot like an algebra 2 problem. Divide by 3, you can take the square root of both sides, so don't forget plus or minus. And then what happens when you try to take the square root of a negative number? Well, we could take the square root of a fraction with a little bit of work, but the square root of a negative number gives you an imaginary solution. So imaginary solutions are not going to show up on a standard real-world coordinate plane. So this one, I can see from the algebra, has none. So go ahead and pause the video, graph that in a calculator, and see that it doesn't have any horizontal tangent lines. Okay, so let's look at the next one. So again, if I would like to know where this has horizontal tangent lines, I'm interested when the derivative equals 0. And so first I've got to actually find the derivative. So I could do the power rule here, and then the derivative of e to the x is still e to the x times by 4 times by 4. And let's figure out if it ever has a horizontal tangent line. So I could set it equal to 0. And then I could do that. And now we still got to move forward here, so we haven't reviewed how to solve an exponential equation yet. But let me go ahead and flip these around. But we can do that with logarithms. So I could take the natural log of both sides. Okay, and you might say, why in the world would you do that? Or how do you know to do that? And the reason is, with natural logs, if this is an exponent on something I'm taking the log of, this can come down out front, which that's pretty significant because that's what I'm solving for. Right? So I'm taking the variable in the exponent and bringing it out. So what I did there in red is a common trick. Taking the log of both sides allows you to bring that exponent down. And in calculus, it's almost always natural log. Natural log of e is just 1, because this is saying e to what power gives you e, so x times 1. But the problem with this is you can't take the log of a negative number. If you remember what logarithm graphs look like, they look like this. And so you would say the domain doesn't exist for negative numbers. So that's one way you would know that. Or you could just think about this is saying e to what power, because this is base e, would give you negative 1/4. And there's no way to make that happen. So again, we get another one where that doesn't happen. So from the algebra, I can see that this is never going to have a horizontal tangent line. Never is the instantaneous slope 0. So again, please pause, practice using your calculator, graph it, and see that there's no horizontal tangent lines. There's nothing where the slope is temporarily 0 like they were on this graph. All right, and then last one, still trying to find horizontal tangent lines. So I think you probably got an idea of how to start this off now. Horizontal tangent lines will occur when the derivative is 0. So if I took this with the power rule, bring the power down, lower the power by 1, and then this. Okay, so I'm using some of those things we talked about at the start of this video. And then, so this would be like, for any value of x, what is its slope? But I want to know what value of x has a slope of 0. Okay, so now, maybe this looks a lot less like an algebra 2 equation, but maybe a pre-cal trigonometry equation. I could take a couple steps and solve this for sine x. And if this is where sine x equals 3/2, and I'd like to know where x equals that, I could do inverse sine, or I just think about it manually. What values on the unit circle have a sine value of square root of 3/2? Okay, and the positive ones, so this would be like pi/3 and 2pi/3. So down here it's also square root of 3/2, but these would be negative, so those wouldn't count. And technically, I guess you could go all the way around and find an angle coterminal to this, and it would be a solution too, but this problem in the direction said only think about one revolution. So one trip around the unit circle, this and this have the right values. All right, so for this one, if you want to check this one in your calculator, you can graph it, and then you should probably change your window settings so that these are the only x values you're looking at. And you'd want your calculator to be in radian mode, because 2 pi is a radian, and you should see that it has a horizontal tangent line twice, and the x values are going to be those two. So pretty useful skill. You can see that sometimes we look at it graphically, and sometimes we have to look at it algebraically, but you have to know those first couple pieces there. You have to know, why am I finding the derivative, and why am I setting the derivative equal to 0? If you don't understand why we're doing that, it doesn't really matter too much that you can do the step after step after step after that. So make sure that you understand that, and if not, please ask for clarification. So that'll be the end of this video, and good luck.